In this lesson, you will learn how to convert complex numbers from rectangular to polar form and from polar form into rectangular form. So first off, let's review what a complex number is. A complex number is a combination of a real and an imaginary number in the form a plus bi. A and b are real numbers, and I is the unit imaginary number, which is the square root of -1. The values of a and b can be 0, but they don't have to be. Here are some examples of some complex numbers. 2 plus 3i and 1 minus 5i both have real and imaginary parts. Negative 2.3i is an imaginary number where a was 0 in the complex number, and 5 is a real number where b was 0 in the complex number. Now, complex numbers can be plotted on a graph. For example, suppose I would like to plot the point z equals a plus bi. It's a point, a units along the real axis and b units along the imaginary axis. And so it would look like that in rectangular form. If I wanted to write it in polar form, I would need r, the distance from the pole to the point, and theta, the angle of rotation off the polar axis. Now you know that the cosine of theta is a over r, and therefore a equals r cosine theta. Similarly, the sine of theta is b over r, and therefore b equals r sine theta. You've seen these several times in the last few days. Now, a is r cosine theta, and b is r sine theta. So I can substitute those into my complex number, and I get z equals r cosine theta plus I times r sine theta. So now we have the complex form of that point. What I'm going to do at this point is simplify things a bit. I'm going to factor out the r. So I have r times cosine theta plus I sine theta. And then I'm going to use the letter c to stand for cosine and s to stand for sine. And I'm going to write z equals r cis theta. What you need to keep in mind is that r cis theta means r cosine theta plus I times r sine theta. Just a reminder, z equals r cis theta means z equals r cosine theta plus I times r sine theta. R is called the modulus of z. Theta is the argument. And if you would like the magnitude of the complex number, that's r. Okay, so here's an example. I'm going to transform the complex number 1 minus I into polar form. So here's my point. It's 1 unit over and 1 unit down. That means that the distance from the pole to the point is 1 squared plus 1 squared, and then you take the square root of 2. The angle theta is pretty big. Inside the triangle we have a 45-degree angle. That means outside it there's 315 degrees, or if you prefer 7 pi over 4 radians. And that means this complex number is the square root of 2 cis 315 degrees, or square root of 2 cis 7 pi over 4 radians. All right, another example. Let's say I'd like to transform z equals the square root of 3 plus I into polar form. First off, there's the point. Square root of 3 units over, 1 unit up. That means the hypotenuse of that right triangle is 2, and there is an angle theta. Theta has to be 30 degrees because the sine of theta is a half, and of course we know that the angle that has the sine of 1/2 is 30 degrees, also pi over 6 radians, and so z equals 2 cis 30, or 2 cis pi over 6. Again, this point, -3 plus 4i. I've gone -3 units over, 4 units up. I'll give you a moment to think about the hypotenuse. Of course, this is a 3, 4, 5 right triangle, so r is 5. And then I want the angle. Well, that's theta. If I look at its reference angle, that's inside the triangle, and if I use the opposite and adjacent sides, I could use the tangent of the reference angle theta is 4 over -3. And see, the 126.87 degrees is more than an acute angle. That is in fact the angle I'm looking for. So z equals 5 cis 126.87 degrees. If you convert that to radians, it's 2.21 radians. Okay, this one's a little different because all I have is the complex number z equals I. I just have the imaginary part somewhere on that axis. 1 unit up, I've rotated 90 degrees or pi over 2 radians. So this is z equals 1 cis 90 or z equals 1 cis pi over 2. And this is what it looks like if I just have the real part. Gone 4 units over, so r is 4. Theta is 180 degrees or pi radians. And so I have 4 cis 180 degrees or 4 cis pi. All right, so let's go the other way. This time I want to go 8 cis 150 degrees and I want to turn it into rectangular form. You have to remember that 8 cis 150 is the same as 8 times cosine 150 degrees plus I times sine 150 degrees. Now, cosine of 150 has a reference angle of 30 degrees, and sine of 150 has a reference angle of 30 degrees. And of course, you know the cosine of 30 is square root of 3 over 2, and the sine of 30 is a half, but when cosine's in the second quadrant, it's negative. And I just need to distribute the 8, and I get negative 4 root 3 plus 4i. All right, the next one. I'm going to spread this out. Instead of writing cis, I'm going to write cosine 45 plus I sine 45. Of course, the r is 4. Now, cosine and sine of 45 are both square root of 2 over 2. And then I multiply it across by 4, and I get 2 square root of 2 plus 2i square root of 2. It's customary to write the I in front of the square root sign if a square root sign exists. Okay, 2 cis 0, spread it all out, so it's 2 times cosine 0 plus I sine 0. Cosine of 0 is 1, sine of 0 is 0, and that just leaves you with 2 plus 0i. And finally, we've got the 11 cis 247, so that's 11 times cosine 247 plus I sine 47. Distribute the 11, take out your calculator. You end up with about negative 4.3 minus 10.13i. All right, now, you can also do operations with complex numbers, and it's not too hard at all if they're in polar form. So first I'm going to derive for you a formula for multiplying two complex numbers in polar form. So I have z1 and z2, and this is what they would look like in polar form, right? I've got r1 cis theta 1 and r2 cis theta 2. I spread them out. And now I'm going to derive for you a formula, so I'm going to do a little algebraic manipulation. I'm moving the r1 times r2 out in front, and then multiplying cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2. So that's just the commutative property. I move things around a little bit. Now I'm going to expand out those two binomials by multiplying them. You can take a moment and just see that you believe me. I multiplied cosine of theta 1 times cosine of theta 2. I multiplied cosine of theta 1 times I sine theta 2, and then I went to I sine theta 1, multiplied it by each of the two things in the second binomial. Now, notice I have I squared there, and I squared equals negative 1. So I'm going to end up with minus sine theta 1 times sine theta 2. I moved things around a little bit, and I grouped them so that the terms that did not have an I in front of them ended up together, and the ones that did have an I ended up together, and I factored the I out. Cosine theta 1 times cosine theta 2 minus sine theta 1 times sine theta 2 is the same thing as the cosine of theta 1 plus theta 2. So that's the thing on the left. Then I got the I that's circled in orange and put it in front. And then I have sine theta 2 times cosine theta 1, sine theta 2 times cosine theta 2. That's sine of theta 1 plus theta 2. And so this is just R1 times R2 cis theta 1 plus theta 2. And I just noticed that in the previous line, I should have had sine theta 2 cosine theta 1, sine theta 1 cosine theta 2. This 2 should be a 1. All right, so using that formula, let's see how it works. If I want to multiply those two complex numbers, I'm supposed to multiply R1 times R2. In this case, that's 3 times 2. And I'm supposed to add the two arguments, the 80 and the 20. So I get 3 times 2 cis 80 plus 20, and that's just 6 cis 100. And that's it. That's how you multiply them. So take a moment, try multiplying the next one. See if you can do it in your head. All right, so you've got 4 times 3 out front, cis, and then you're going to add the 100 and the 50. And you should get 12 cis 150. In our next class, we'll look at dividing and adding and subtracting, also raising to powers. But today we're just going to look at the multiplication. All right, and that's it for your pair deck. So now what I'd like you to do is I'd like you to log on to ClassKick. You will see an assignment that says 15.4 ClassKick number 1, dated today, January 13th, 2021, and I'd like you to do those problems. So please show enough work that I can tell what you're doing, as well as you're writing your final answers. And like usual with ClassKick, I have turned on the self-grading, but if you don't type it in exactly the way it's expecting it, even if you have the right answer, it may not record it as correct. So don't worry too much if it's not correct when you type it in. If you're sure your work is correct and you've shown your work, then if it is correct, it'll be fine. All right, that's it, and I hope you have a good day.